Arranging atoms, one by one, the way we want them. This was an invited talk delivered at the 18th International Conference on Nano-Micro-Engineered and Molecular Systems held in Jeju, South Korea, May 2023. Before I begin, I would like to express my gratitude to the conference organizers and planners that made this possible, and for the generous invitation to speak. As well, I would like to highlight that the work I have been invited to speak about has been advanced by a substantial number of people whose names are listed here. The current core contributors to this project are listed on the left, and it is my honor to share with you the impressive results that these researchers and scientists have been able to accomplish. The overarching theme of this work is encapsulated by this quote from Richard Feynman. But I am not afraid to consider the final question as to whether ultimately, in the great future, we can arrange the atoms the way we want. The very atoms, all the way down. What would happen if we could arrange the atoms one by one the way we want them? We are all familiar with Moore's law and the shrinking of transistor device dimensions. With shrinking transistors, we can fit more and more into the same physical footprint, and the transistors get cheaper and cheaper. However, the same physics governs a large transistor and a small transistor. There's no operational difference as we scale these things down. But when we get to the level of single atoms, the operational physics changes. We are no longer in the realm of continuous classical physics, but in a strange world governed by quantum mechanics. Feynman's question becomes quite prescient. What would happen if you could arrange the atoms one by one the way you want them? Here are a few examples from the literature that attempt to answer this question. There are many theoretical investigations such as these, attempting to predict how materials will behave and how we might be able to harness the emergent quantum properties for future technological advances. But this will not be a talk about quantum mechanics. Quantum mechanics has a reputation for being difficult, and you might breathe a sigh of relief hearing that we will not delve deeply into it here. However, I want to talk about something much more difficult. And that is, how do you, not in theory, but in real life, put the atoms where you want? In 2016, some members of the group published a paper elaborating the idea that you could use the focused beam in a scanning transmission electron microscope as a manipulation tool. The beam is focused down to the scale of the atoms. It has a substantial amount of energy, and it can be used to drive material transformations on the atomic scale. A few years later, we published a review article summarizing many experimental demonstrations of precisely this kind of precise manipulation of materials using the electron beam. But it has been long known that the electron beam can be used to drive transformations. Indeed, hydrocarbon deposition and beam damage have been continual challenges in electron microscopy. Rather, it is that they have been substantially mitigated that we can now begin to turn our attention to subtle changes that the beam can bring about, and try to gain some level of control over what happens. Here are a few examples. From 2005 to 2013, Van Dorp et al. Published a series of papers describing how they were able to perform electron beam-induced deposition in a stem. This is typically performed in an SEM with lower resolution, but the sharp focused beam in the stem and using single-layer graphene as the substrate, they were ultimately able to deposit material molecule by molecule. This was in no small part enabled by the great lengths they went to ensure stringent sample cleanliness. In 2012, Cretu et al. Showed that few atom clusters could be separated from their parent nanoparticles and dragged a short distance across a graphene surface using carefully controlled E-beam irradiation. In 2015 and 2016, at Oak Ridge National Laboratory, we were also investigating beam-induced transformations. In this example, the letters OR and L were able to be crystallized one atomic plane at a time. It is from this background that the idea of the atomic forge was born. In principle, one could use the E-beam as a fabrication tool to reach down to the level of the atoms and put them where you want. It is visionary, it is ambitious, but it is also necessarily vague on many important details. What transformations will we drive? What materials will we use? And what signals should we be looking for? We now have a number of years of experience working in that direction, and the challenge ahead of us has become clearer. In this talk, I would like to lead you through a number of experiments and present a new picture of what the future of atom-by-atom fabrication will look like. In particular, I would like to introduce the concept of the synthoscope. where we combine synthesis approaches to material deposition and growth with what we have learned about atomic manipulation. Can we think about performing synthesis at the scale of a single atom? What would this mean? We begin by looking at e-beam-induced deposition. This is a well-known top-down approach to locally depositing material on a substrate using an e-beam. The substrate shown here is graphene. We then use a gas injection system to flow a molecular precursor gas across the substrate. We then irradiate some area with the e-beam and move it where we want to deposit material. The e-beam dissociates the precursor gas, which becomes chemically reactive and then bonds to the substrate, forming a deposit site. In this way, arbitrary structures can be built up, akin to 3D printing on the nanoscale. But we would like to scale some process like this down to where we can deposit single atoms where we want. So let's consider it. Here are a few examples of different molecular precursors. We notice, of course, that they are all molecules and not single atoms. The e-beam approach to deposition requires molecules as precursors because the e-beam has to first dissociate the molecule, that is, break it apart, to create a chemically reactive molecular fragment at the desired location. If we want to deposit an atom, what is it exactly that we want to do? If we were to put a single atom on an atomically pristine substrate, this is just an atom. It can easily diffuse around the surface with a little bit of thermal energy. This is not what we typically think of as deposition. The e-beam deposits, for example, do not diffuse around on the substrate surface. They have strong chemical bonds that hold them in place. But even if we ignore the fact that we do not have a clear picture of what deposition should look like at the scale of an atom, we have another problem. If we supply a chemically pure precursor material, single atoms, to the sample, there is nothing to dissociate. The mechanism that e-beam is using to drive deposition requires molecular precursors, not atomic precursors. So the e-beam approach to deposition cannot physically scale down to single atoms. On the face of it, it seems like a rather hopelessly intractable problem. Nevertheless, there is a way forward, and the solution offers itself by grappling with the problem of exactly what is it that we want to have happen. We cannot ignore the fact that we do not have a clear picture of deposition on the single atom scale. Once we realize that we need strong chemical bonding between the substrate and the atom, and that we cannot modify an atom, we come to the inevitable conclusion that we must modify the substrate. What will this look like? Here's a conceptual model. We start with the graphene substrate, and on top of the graphene, we have our source material. We would like to get an atom from the source material into the graphene lattice. So we take our electron beam and drag it across the graphene. If we operate the microscope with an accelerating voltage above the displacement threshold for graphene, we will start to eject carbon atoms from the lattice and form vacancies. Then, we move the beam back onto the source material and sputter single atoms off of it. These atoms can then diffuse around on the graphene surface, and when one of them reaches the vacancy site, it can form strong chemical bonds with the undercoordinated carbon atoms. We have then achieved deposition of a single atom. It sounds plausible, and there are compelling drawings, but talk is cheap. Does it really work in practice? The answer is yes. Here are images of the first demonstration published in 2017. This is a single layer of graphene with some contamination on the surface, the bright areas. In the contamination, we almost always find some silicon atoms. The beam was positioned about a nanometer away from the contamination and a small hole or defect was formed. The beam was then scanned over the contamination and a silicon atom was ejected from the contamination and attached to the graphene at the damaged location. Here's a second example. A small hole is formed, one silicon atom attached, and then a second silicon atom forming a dimer. This was very exciting. We are able to attach single silicon atoms to graphene. But how about other types of atoms? The silicon atoms were just found on the graphene surface. Maybe we can put atoms on the graphene surface that we want to put in the lattice. The first element we tried was platinum. We used e-beam to deposit platinum lines with an SEM, and then found some platinum atoms in the surrounding contamination, and were able to attach them to the graphene defect sites created by the e-beam. Next we tried chromium, this time using an e-beam evaporator to put chromium across the whole sample. Then we went through an extensive list of elements that we had on hand for the e-beam evaporator, illustrating the general applicability of this approach. So we can indeed deposit many different kinds of atoms, at least in principle. However, this does not look like a reliable fabrication process. To move this in the direction of being a useful tool for fabrication, we need to address several problems lurking in the background. When you Google graphene, what you will typically see is rendered images of a perfect hexagonal lattice like this, or you will see carefully cropped images with a handful of atoms. However, in the real world, graphene looks more like this. The majority of what you're seeing is not the graphene, but the surface contamination. If you have a nice clean sample and you zoom in, you can find these small dark areas where we have atomically clean graphene with nothing on the surface. These bright nanoparticles are the chromium we evaporated onto the surface, and the rest is representative of the typical contamination found on graphene. So, we have several rather challenging tasks ahead of us. First, we would like some kind of cleaning procedure so that we can obtain and maintain atomically clean graphene in the microscope. Graphene gets dirty just from exposure to the air, so this needs to happen in the microscope vacuum chamber. Second, we don't really want our source material to be adhered to the graphene surface. It's difficult to imagine how one would use this approach to atomic fabrication if you have to deposit a bunch of unwanted material on the surface just to put an atom where you want it. Third, I've not really belabored the point yet, but when we create our vacancy, it needs to remain there until the source atom comes along and binds to it. I will explain why this becomes a challenge a bit later. Finally, all this effort is not really just to put one atom somewhere. We want to be able to put many atoms where we want. We want to pattern atoms, and this is not going to be done by hand. We need some automation to stand on. In short, a proof of principle is not manufacturing. There is still a long way to go. Let's look at the first problem, getting the graphene clean. There are many papers detailing various methods for cleaning graphene. The reason why they are so numerous is that despite all our efforts, graphene remains dirty. In fact, graphene gets dirty in just a few minutes on exposure to air. So, having a variety of cleaning methods to fall back on is advantageous. In the publication shown here, we demonstrate an in situ cleaning technique where we rapidly heat the sample to remove the surface residue. With this technique, we can go from the level of contamination shown here to almost perfectly clean graphene. All of the uniform gray intensity is clean graphene, with a few stragglers left that show up bright in this imaging mode. This looks great, but there is slightly more going on than meets the eye. Here's an example of a sample that starts out coated with visible contamination. After heating, much of it becomes clean, but if you zoom in, you start to get hydrocarbon deposition. So even though the graphene appears clean, there are still mobile hydrocarbons that we can't see that interfere with us. Here I was examining their behavior. In Area 1, I acquired a video for 42 seconds. The first and last frames are shown. All the areas that were clean on the first frame, I tinted orange on the last frame so we can clearly see where the hydrocarbon deposition occurred. It occurs everywhere. Then I acquired a similar data set in Region 2. The first and last frames are shown. What we notice is that growth only occurred on one side of this barrier. Looking back at the overview image, we can see that the difference is that one side of the barrier is a region that is completely enclosed by a continuous barrier that encircles the graphene, while the other side is connected to channels of clean graphene off to infinity. To leverage this new knowledge, I selected an area of graphene I wanted to work in that was almost enclosed and deposited a wall to seal it off from the rest of the graphene. I then acquired another video across the deposited barrier and indeed was able to create sections of graphene that remained free of deposition at elevated temperatures. The mobile hydrocarbons also appear to desorb over time, so that if one is patient enough, the deposition will gradually stop. At this point, we have a way to clean graphene and maintain cleanliness at elevated temperatures. Next, we are going to have a look at the diffusion of vacancies at elevated temperatures. Here, we are interested in the final step of this process, of attaching impurity atoms to arbitrary locations. We want to be able to create a single vacancy so that we can attach an atom to it. We also have in mind that we will ultimately want to automate this process, so we began by automating the drilling of holes in graphene in the hope that we would be able to push the dimensions of the smallest holes down to just a single vacancy. We developed a data acquisition and control platform that is able to control the microscope scan coils to enable arbitrary scan patterns, as well as read detector output to enable real-time feedback control and decision-making. For the automated milling approach, there are two modes. In imaging mode, the beam is scanned in a regular raster pattern to acquire a standard image of the sample. When we are ready to start milling, we switch into the milling mode, and the beam is then scanned in a small spiral centered on the location where we want a hole. This allows us to create a small image of the sample that can be updated with each pass of the spiral. The majority of the dose is concentrated at the center of the spiral where we want to create a hole, but the extended tails of the dose profile allow us to obtain a larger image of the local structure. We then use the average intensity of the spiral image as a feedback control and set a lower threshold that indicates when a successful hole has been milled. When this threshold is hit, the computer automatically advances to the next position, and in this way we can pattern holes in graphene in a fully automated fashion and start to get some statistics on how this process proceeds. We immediately ran into some surprising results. The hotter the graphene, the more dose it took to mill a hole. That's what this plot is showing. We expected that the greater thermal excitation would lead to slightly easier milling, as is predicted by intuition and the most detailed theoretical treatments. What this data shows is that the opposite is happening. Perhaps a better illustration of this effect is shown here. We are comparing an image acquired at 900 degrees Celsius that delivered a dose of 10 to the 10 electrons per square nanometer during the acquisition. There is no observable damage to the graphene. In contrast, this image was acquired at room temperature with an order of magnitude less dose, and the graphene is almost completely destroyed. At first we considered that it could simply be healing. Perhaps some residual hydrocarbons can still make it into our corrals and heal the graphene, making it more difficult to mill. As we increase the temperature, we are increasing the supply of these residual hydrocarbons, which increases the likelihood for healing. It sounds plausible, but what does the data show? Let's look at some examples. In each of these examples, we successfully milled a 5x5 array of holes, and then acquired the final overview image shown. What we see is that at lower temperatures, there is significantly more healing than at higher temperatures. This means that if healing is indeed playing a role, it is counteracting this trend. In other words, if healing did not happen at all, this trend would be more pronounced, not less. Now this was quite a puzzle, and we were baffled for some time until we performed this experiment. Here we decided to mill just one hole at the center of the image, but periodically during the milling process we acquired a full image frame to see what happens to the adjacent areas of the graphene during this process. What we found is that chains of defects grow into the imaged area and branch toward the milling location. When they finally grow into the milling location, then we are able to form a hole. If we zoom in and look more carefully at the structure of these chains, we find that they are primarily structured like a stack of reconstructed die vacancies. We are indeed creating many vacancies while trying to mill, but these vacancies diffuse away from the milling location so fast that we cannot even see them. But these vacancies have some probability of meeting each other, merging together, and restructuring into a reconstructed die vacancy. This structure requires much more energy to diffuse through the graphene lattice, and at the temperatures we're working with here, they are essentially fixed in place once they form. They also create a strain field in the surrounding lattice that encourages the vacancies to diffuse to the top and bottom of this structure to relieve the compressive strain, which ultimately results in the sequential buildup of long defect chains, one vacancy at a time. Well, that was all handy to know, that we didn't break any laws of physics and that this puzzle could be resolved in a satisfactory manner, but this is not at all helpful for putting atoms where we want. It would be much to our advantage if the vacancies would stay where we put them. The faster they zip through the graphene lattice, the more troublesome they become for us. But we now have thousands of examples of holes being milled, and as we carefully looked through this data, occasionally we found examples like this. This appears to be a silicon trimer that was spontaneously incorporated into the lattice while it healed. This got us thinking. What if we somehow supply atoms to the milling location while we are milling? Maybe we can attach impurities to the vacancies the moment they are formed. And if we can somehow stabilize the vacancies, this may give us a little more time for the impurity atom to attach. What we would like to do, then, is to somehow deliver atomized material to the region of interest. Since we are already, at this point, operating on a heater chip, maybe if we just put our desired source material on the graphene surface, some of the atoms will be thermally freed from the parent nanoparticles and diffused to where we want them. We modified our feedback control platform so that we could set two thresholds, one for holes that show up as a dip in intensity, and another one for dopants that will show up brighter than the graphene. We then prepared a bilayer graphene sample to help suppress vacancy diffusion and evaporated chrome onto the surface. Here's an overview image of the sample. The dark areas are clean, twisted bilayer graphene. The green nanoparticles that are all over the surface are the chrome, and a bit of foreshadowing, we also had a few spurious copper nanoparticles scattered across the sample. Then we heated everything up to around 1000 degrees Celsius and started to see impurity atoms spontaneously attaching to the graphene wherever we looked. We fired up the patterning platform, and we were able to start patterning atoms in small clusters into the twisted bilayer graphene. Unlike the initial demonstrations of atomic insertion, where we had to be very close to the parent nanoparticles, we can now pattern wherever we like in arbitrary patterns. But it turns out most of the inserted atoms were not chrome like we thought they would be. Instead, they were copper atoms. Incidentally, in our original proposal, we had rather boldly claimed that we would be able to pattern atoms as shown in this rendering. It wasn't until after we had begun writing up the final summary document that we were able to start patterning, and in the last week, we were able to acquire this data to include in the report, hot off the microscope. This was a fantastic breakthrough, and the next obvious question is, what happens if we vary the temperature? We performed these experiments at a bunch of different temperatures, and what you're looking at here is a bar plot summary of every outcome as a function of temperature. A hole is represented as a 0, a dopant is represented as a 1, and for each temperature, the bar height represents the average result. We see very clearly that at about 1100 degrees Celsius, we switch from mostly milling holes to inserting dopants. This is right around the melting temperature for bulk copper. So indeed, we are evaporating or atomizing our source material, it is diffusing across the sample, and we can then pattern these atoms into the substrate. Chrome has a much higher melting point than copper, so we are getting copper atoms, but the idea works. And this started us thinking about what we are trying to do from a different perspective. Here, I want to lay out the case that what we really want to do is synthesis in the stem at the scale of an atom. What we want is the synthoscope. Let us look at the progression. We started with E-beam induced deposition. Van Dorp was able to push this technique to the physical limit, ultimately demonstrating molecule by molecule deposition. We also discussed why this technique can't quite get down to atom by atom deposition. To get down to single atom deposition, we have to abandon the operational principle of E-beam induced deposition. Instead of dissociating a precursor gas, we have to damage the substrate. We showed that this works for silicon and a long list of other elements. But it only works very close to the reservoir of source material, and we are using the E-beam to both damage the substrate and sputter atoms from the source material. If we use thermal evaporation, or atomization, it appears we can supply these atoms from a longer distance and start to perform automated patterning at the single atom scale. In this picture, however, we still have source material sitting on the graphene surface. We would really like this to be located somewhere else, both because it cleans up the graphene and because we would then have independent control over the temperature of the graphene substrate as well as the source evaporation temperature. Our ideal picture then looks something like this. We have a perfectly clean graphene substrate. Atoms of our choice are evaporated from a separately controlled source onto the surface where they can continuously diffuse around. Only when our beam comes down and makes a modification do we obtain the result we want. This is starting to look like a special case of synthesis, where the global environment is prepared, substrate temperature and supply of source material, but no synthesis reaction occurs until the beam is turned on. It is the beam sample interaction volume that specifies where this reaction will take place. It is a synthesis chamber the size of an atom. It is, of course, much easier to say than to do. How would one pull it off in reality, where we have pesky things like a fixed pole-piece gap in the microscope, ultra-high vacuum compatibility issues, existing hardware, and a non-infinite budget? Here's one possibility. We use the existing electrical holder cartridge and design a new insert for it that will hold both a MEMS-style sample chip like the heater chips we have been using, as well as hold a resistive heater filament that can be soldered onto the end of the insert. The source material could be deposited on the heater filament and then evaporated from it in situ. Because we are interested in ultimately making use of these fabrication capabilities, we have also put a significant amount of effort in developing STEM-compatible devices that are fabricated on the wafer scale. These devices have an electron-transparent window at the center, which allows high-resolution imaging during operation and will allow us to use the e-beam to modify the device at the atomic scale. An alternative strategy could be to perform in-situ pulsed laser deposition. In this concept drawing, we have multiple evaporation targets, and the laser could simply be aimed at whichever source material we want and allow us to switch materials on the fly. I am happy to report that we do not just have drawings. We have in fact built a prototype evaporation platform on which those drawings were based. The evaporation platform is an attempt to address this step of our atomic deposition process. We need to get our source material off the surface of the sample, but still be able to supply it in an atomized form when desired. Here is the conceptual schematic showing the different parts and how it assembles together, and a picture of the assembly about to be sent off on its maiden voyage into the microscope. This is a picture of it sitting in the pole piece of the microscope with the light on. Then we switch the light off and activate the heater filament. So far so good, the heater works. Now the real test. We put a thin coating of tin on the heater filament and put it back in the microscope with another twisted bilayer graphene sample. The graphene is sitting on its own heater chip, so we can heat it independently from the filament. Here we've heated it up to clean it, and in this dotted oval we took a few high-resolution images and introduced a few damage sites shown in the boxes. Then we heated the filament. These are the before and after images. The little bright spots are the tin that has been deposited onto the sample. Most of it has attached at step edges or wrinkles, but we do see some bright spots where we damaged the sample. On the left here, we have the vacuum reading through time as we increase the power output of the filament. The more power, the higher the vacuum spike, indicating we are evaporating more material. On the right are a couple of higher resolution images of the bright regions. It appears we have synthesized 2D tin nanoflakes. We are still working on figuring out the exact structure of these nanoflakes, but we have our first in-situ growth. Since we have independent control over the substrate temperature, we can change it on the fly. The initial deposition was performed with the substrate held at 500 degrees Celsius. I was quite curious to see what would happen to the deposited tin if the temperature was increased, so I heated it to 900 degrees and then acquired these images. First, we see highly mobile tin atoms decorating the step edges. A few minutes later, we see that tin nanoparticles have formed. Next, we are going to zoom into the circled region here. We can now more clearly see the tin atoms along the step edge, and of course, there is this curious line of atoms extending out from the step edge. What I did was create a small subscan box and position it at the step edge, so only that area was being irradiated. Then I manually moved the box across the graphene to write a line of tin atoms. I paused to take this image and then continued writing a bit more. Here's a diagram of the process. The beam is confined to the irradiated region. Carbon atoms within this region are ejected from the lattice, and highly mobile tin atoms are able to take their place. As the bright tin atoms appear in the subscan region, we advance the subscan box to expose more of the graphene. The process is continuous and easily amenable to automation. There are many questions still to answer and a vast playground to enjoy. We have only taken the first tottering step toward the synthoscope idea, but it's worth pointing out a critical feature we have employed throughout this presentation without explicitly naming it. That is, the chamberless synthesis environment. This is the perturbed region of the sample where the beam locally creates an environment that is very different from the surrounding region. This disturbance is what prompts a material transformation locally instead of globally. We can view e-beam-induced deposition as a special case of this process. The global parameters are set by introducing a molecular precursor gas at a particular partial pressure, but nothing happens until the chamberless synthesis environment is created by e-beam exposure. The conditions for spontaneous material transformation are not globally available. In the STEM, this concept can be scaled down to a single atom, provided that we let go of the specific reaction used in e-beam-induced deposition and speak more generally about a chamberless synthesis environment. This work was performed at the Center for Nanophase Material Sciences, which is a Department of Energy user facility. With an approved 2-page proposal, you can gain access to equipment and staff expertise free of charge. Links to the publications referred to in this presentation can be found in the comment section below, as well as a link to download these slides from SlideShare.